You, me, the Earth, and all the planets of the solar system are currently at the center of a strange cloud of colossal proportions. A cloud called Oort, which is spherical. Hidden in the dark space between the stars, this immense scattered bubble, this vast diffuse cloud whose precise boundaries are still unknown to us, remains entirely out of our sight for now. And yet, even though no one has ever directly observed it, we know it's there, because it occasionally reveals itself to us when parts of its whole come to visit us, in the form of comets that enter the inner solar system and, getting too close to the sun, begin to evaporate. In fact, we believe that many of these blocks of ice and dust come directly from this cloud. It's even their recurring presence that led us to suspect its existence. In the 1950s, the astronomer Jan Oort, who gave his name to the cloud and lost hundreds of hours of sleep over it, tried to solve a troubling mystery. How can we explain the presence of so many comets today when our solar system has existed for 4.6 billion years? And those that come to visit us, after a few dozen or even hundreds of passes at most near our star, all inevitably end up being blown apart, broken up by the power of the sun, or at the very least expelled from the solar system, because their highly elliptical orbits are unstable in the long term. It is to explain the undeniable and enigmatic presence of these comets that people began to suppose the existence of a vast reservoir. A reservoir of cometary core material that, over dizzyingly long periods of time, would have remained far from the sun's heat, hundreds of billions of kilometers away, following vast, stable, and generally circular orbits. Thus, by studying the elliptical orbits of so-called long-period comets, which can take tens or even hundreds of thousands of years to orbit the sun, it was realized that they come to us from absolutely every direction in the sky. And from the data collected from the study of their trajectories, which are not aligned with the plane in which all the planets of the system are located, we were able to start guessing the spherical shape of this icy cloud, and the shell all around us that supplies us with cometary nuclei, and above all, to appreciate its truly gigantic dimensions. To grasp the immensity of this strange bubble, let's start by setting the scale of the scene it completely surrounds, by going to the center of the system, to the surface of the sun, which a photon has just now left. For this particle of light traveling at the staggering speed of about 300,000 km per second, it takes a little over 3 minutes of travel to reach Mercury's orbit, 6 minutes to pass Venus's orbit, and about 8 minutes and 20 seconds to cross the 150 million kilometers separating the Sun from our planet's orbit. 12 minutes and 30 seconds after its departure, our photon reaches Mars's orbit. Then, an additional half hour is needed to pass Jupiter's orbit. After that, you have to add twice the time already elapsed to reach Saturn's orbit, then double the travel time again to reach Uranus's orbit. A little over 4 hours after leaving the surface of the Sun, our light particle now ventures beyond Neptune. Entering the Kuiper belt immediately after, a thick disk rich with billions of small rocky or icy objects, hundreds of millions of comets and asteroids, and a few planets such as Pluto, which has been dethroned. And our photon continues to speed through this belt, where the bodies begin to tilt sharply. Because unlike the planets and other asteroids of the inner solar system, which all orbit our star within the same plane called the ecliptic, when we venture into these remote regions, the apparent order, the alignment along a single plane, wavers. And during the 3.5 hours needed to cross the Kuiper belt, many of the trans-Neptunian objects we now encounter have highly inclined orbits. Our hypothetical photon, meanwhile, continues to speed through space. Nearly 2 more weeks of travel at the speed of light, the maximum speed possible in the universe, are still needed before hoping to reach the inner edges of the Oort cloud. Another way to grasp the overwhelming, absolutely extraordinary, enormous distances that separate us from it is to remember how long it would take the Voyager probe. One, the object made by human hands, currently the farthest from our planet, and which is speeding at 17 kilometers per second toward this cloud. It would take at least 5 centuries before reaching its inner edges, at the vague and diffuse boundaries. At this point, the probe, more than 300 billion kilometers away from the sun's warmth, will have long since run out of energy, unable to send us any information about these vast and mysterious regions. We know from studying the trajectories of comets that reach us that the Oort cloud is, in a way, split into two distinct parts, giving it the appearance of a giant cosmic shell. In the first hundreds of billions of kilometers of its interior, this cloud initially takes on a roughly toroidal shape, which is thought to contain 10 to 100 times more cometary nuclei than the spherical outer part of the cloud. It will take Voyager 1 at least 2,500 years to cross this thick torus, within which the orbits of objects continue to tilt, and which continuously supplies material to the outer envelope of the Oort cloud. From there, cometary nuclei are ejected out of the system, or even propelled toward its center, near the Sun. Although less dense than the inner part, the spherical outer region of the cloud could still contain, spread out over an absolutely staggering volume of space, up to 5 times the mass of our planet, in the form of trillions of objects, frozen debris, icy dust, water, methane, ethane, ammonia, and above all, hundreds of millions of asteroids and trillions of cometary nuclei, more than a kilometer in diameter. Each of them is on average about 10 million kilometers away from the others, so no illustration will ever be able to convey the staggering emptiness of these fields of dust and blocks of rock and ice, drifting in a void as cosmic as it is astonishing. To put it another way, there's nothing to see here. Everything is absolutely bleak and dark. The truly mind-boggling distances separating us from these small dark bodies plunged in darkness explain why our telescopes have so far never managed to directly observe this cloud, even though we've been able to identify objects coming from it or returning to it. For example, in 2013, a comet was identified approaching the Sun, and its orbital period is so long that it will take 740,000 years before it visits us again. Since then, heading toward the Oort cloud, it has cooled down significantly, and its tail has eventually disappeared. Traveling at the speed of Voyager 1, it would take you about 25,000 years, covering a little less than 1.5 million kilometers per day, to hope to cross the entire outer part of the Oort cloud. And finally, to cross the gravitational boundary of our system, which, strictly speaking, includes all the celestial objects orbiting around the Sun. During this long period, as the probe moves forward, it will see the Sun's brightness visually decline, until it becomes nothing more than a pale star among the thousands of others twinkling in the sky, barely brighter than the brightest star in our night sky. On its journey, perhaps Voyager 1 will occasionally encounter one of the trillions of comet nuclei, which, held to the Sun by only the faint force of gravity, surround it like a scattered bubble. Most of the comet nuclei that can be found here have very likely been here for billions of years. They are waiting to be gravitationally destabilized. For the fragile thread that connects them to our Sun to be broken by the passage of another star nearby, or by the tidal effects of our galaxy, which, by disturbing their circular paths, can dislodge them from their slow drifts and send them toward the Sun, where their nuclei will, after several passes, be completely vaporized. Here, with a bit of luck, you might even pass close to one of the many dwarf planets that this cloud contains, certainly, and whose discrete presence seems to manifest itself in the sometimes strange behavior of the bodies in the Kuiper belt, which they seem to disturb from a distance by their presence in the cloud. But what is the origin of these drifting objects, and how did they end up so far from the Sun? To put it simply, the answer to these vast questions lies in a single event: the birth of our solar system. It is believed that about 4.5 billion years ago, during the chaotic period, our star and its planets were formed by the collapse of a giant gas cloud. And as the matter around the newborn Sun began to organize itself into a plane, on the outskirts, part of the disk and the forming planetesimals would have been scattered by the increasingly imposing presence of the young gas giants. Thus, blocks of rock and ice, failed planets, asteroids, and other comet nuclei in large numbers would have been torn from their orbits, scattered, and pushed to the outskirts by the gravitational interactions imposed on them by the masses of the gas giants. All these ejected disk fragments would then have taken on extremely eccentric orbital paths, capable of carrying them to the outermost reaches of the solar system. Then, as millions of years passed, these torn fragments would have experienced, due to the recurring passage of stars and giant molecular clouds nearby, their orbits stabilize, gradually becoming circular, to the point of eventually forming a gigantic sphere, a bubble of debris evenly distributed. Thus, the immense Oort cloud is in a way made up of the remnants, the residues of our now vanished protoplanetary disk. And 4.5 billion years after the formation of our solar system, from the collapsing storm of gas and dust, all that remains is a sphere, a cloud, whose droplets are the frozen cores of comets. And time keeps passing by. In about 25,000 years, Voyager 1 should reach the outer edge of the Oort cloud, the cosmographic and gravitational boundary of the solar system. By then, the probe will have traveled just a little more than a third of the distance separating us from the closest star. It will be 3,000 times farther from the Sun than Neptune is. And once it reaches the vague and diffuse boundary of the outer edges of the Oort cloud, it's even possible that the probe, leaving the cloud, will quickly continue its journey inside another one. In fact, it's believed that this type of bubble is found around most stars. And given their enormous size, it's even quite possible that as they cross paths, these clouds end up touching and exchanging matter. So, these small remnants from the beginnings of our solar system, orbiting billions of kilometers away from us, could also be mixed with significant amounts of extrasolar matter. In fact, it's believed that a considerable part of what makes up the Oort cloud comes from clouds other than the one that formed our solar system. This material from elsewhere could have been torn away by our star in the earliest moments of its life from other protoplanetary disks that formed at roughly the same time and nearby, or even captured by its powerful gravitational field during its journey through space. In this episode, I used a lot of huge numbers, which are monstrously difficult to imagine. And to make it up to you, I suggest you take a small piece of the immensity of Oort with you by mentally building a scale model of this gigantic cloud in your minds. For that, and by the power of thought alone, let's shrink our system so that our sun is just a ball 10 centimeters in diameter. At this scale, our planet is now only the size of a pinhead, a tenth of a millimeter wide, and located 10 meters away. Neptune, on the other hand, is about 320 meters away from here. As for the Oort clouds, they start about 20 kilometers away and end around 1,500 kilometers from here, which is the distance between Barcelona and Berlin. As for the comets drifting in this miniature universe, they are hardly bigger than a small cluster of molecules, moving only a few hundred meters at most per century. Even when greatly reduced, the sizes and timescales still remain somewhat astronomical.